In this section, we're going to solve some systems of equations using the substitution method. Remember from the previous section that there are three different scenarios where your two lines have one point of intersection, no points of intersection where the two lines are parallel, or infinitely many points of intersection where the two lines or the two equations are actually describing the same line. So we're going to see algebraically how to deal with those different scenarios, and you are more than welcome to read that list of steps there at the top of the screen. I'm going to jump right into problem number 1 and solve using substitution. One thing that I like to do when I'm working with systems of equations is to number my equations. So I'm going to call this number 1 and number 2. Sometimes you'll see them labeled as A and B. And when we get to systems of 3 equations, I'll call them 1, 2, and 3. Others will call them A, B, and C. And the substitution process looks like this. You'll notice that the first equation says y equals. And in the second equation, our y value is kind of tangled up in there on the left hand side. So what I'm going to do is I'm going to take the y value that is 13 minus 3x, and I'm going to plug it in or substitute it in here in place of that y value. So let me say, I don't have a lot of space unfortunately, so I'm going to be working horizontally across the screen, and I'm going to substitute equation 1 into equation 2. So instead of writing 9y, I'm going to write 9 times the quantity 13 minus 3x. And then I do still have to write the rest of that equation, so plus 2x minus 8. And that's equation 2. What you're seeing now is the equal sign didn't register, or I didn't put it. 2x equals, oh, I see what happened there. I'm going too fast. Equals negative 8. That's equation 2. What you'll notice now is that the equation I just wrote has only one variable in it, which makes it much easier for us to solve. So let's go through the process of solving this equation for x. I'll distribute multiplication by 9. 90 plus 27 is 117, minus 27x plus 2x still equals negative 8. And then I will combine like terms on the left-hand side, which gives me negative 25x. And I'm going to subtract 117 from both sides, which gives me negative 125 on the right-hand side. And then I'm going to divide both sides by negative 25, which gives me an x value of positive 5. Now I'm going to take this x value of positive 5 and I'm going to substitute it into, or plug it into, equation number 1 in order to find my y value. Solve for y. Okay, so here's equation number 1. Y equals, that's convenient, 13 minus 3 times not just x, but we know that x is a 5 now. So 13 minus 15 equals negative 2. Y equals negative 2. We've got our x value and our y value. It looks like there's only one point of intersection, so we will express our solution as an ordered pair. X comma y is in this problem 5, negative 2. And this is typical that your solution to a system of equations will be presented as an ordered pair. In the next problem we're being asked to solve using the substitution method. You're going to go through the exact same process. Since this first equation says y equals, that's very convenient. I'm going to take all of this stuff and I'm going to plug it in place of this y value. So your new equation will say 4x minus 6 times, and then in parentheses, 1/3 x plus 1/2, close parentheses, equals 7. Be careful, your next step needs to be, after that, your next step needs to be to distribute multiplication by -6. So the substitution process, pretty straightforward. Notice in the previous problem, after we did our substitution, the next thing that I had to do was distribute my multiplication by 9, which is how I got this 117 and the -27x. So it's not a big surprise that after you make your substitution here, you'll be distributing multiplication by -6 to the 1/3 x and to the positive 1/2. This next little subsection of examples puts us into the other scenarios, not just a scenario where we have one solution, but potentially where we have no solutions or infinitely many solutions. So let's see what this next one turns out to be. Let me label these equation 1 and 2. And let's see, it doesn't really look great for, oh, it does look good for substitution. Equation number 2, it doesn't say y equals, it says equals y. So we can immediately take that equation and plug it into equation number 1. Let's do that. Substitute 2 into 1. So that gives us 5x minus 2 times our new y value, which is 5/2 x minus 4. And that's still equal to 8, and that was equation 1 with our new y value substituted into it. And the next thing we have to do is distribution yet again. So let's distribute this multiplication by -2 to both of the terms inside the parentheses there. We've got 5x. Now you could write this as minus 10x over 2, or minus 10/2 x if you want to. And then be careful when we're distributing multiplication by -2, the -2 times -4 is going to change us to a positive. We've got positive 8 there, equals 8, okay? And then notice that this 10 over 2 is going to reduce and turn into a 5. So we can write our equation now as 5x minus 5x plus 8 equals 8. Well, these 5x's are going to cancel, which leaves us with a statement that says 8 equals 8. How often is that true? Give me an x value. How about -2? Does 8 still equal 8? It sure does. What about an x value of 4? Does 8 still equal 8? Sure does. How about an x value of -1,000,000? 8 still equals 8. It's looking to me like we're going to have infinitely many solutions. And that's because these two equations actually describe the same line. I noticed that if I multiply equation 2, if I take equation 2 and I multiply it by 2, I'm going to get an equation that's identical to equation 1, except that the terms are just written in a slightly different order, but otherwise they're the same equation. So how do I express my solution to this? Sometimes the question will be how many solutions are there. In this case, you could say there are infinitely many solutions. But if we want the actual list of solutions, that's going to be a list of ordered pairs. Every ordered pair that's on both of these lines, which are really the same line. How am I supposed to give a list of infinitely many ordered pairs? We can list our solution like this. It's the set of ordered pairs x comma y such that 5x minus 2y equals 8. In other words, our solution is any ordered pair that satisfies that one equation, because any ordered pair that satisfies that equation is going to satisfy equation number 2 also. A lot of solutions to that one. So when you end up with something like 8 equals 8, or 0 equals 0, or 5x equals 5x, that's an indicator to you that there are infinitely many solutions. And then you just need to see, based on the question and how the question is phrased, how do they want the final answer presented. In equation number 6, one of our equations does say y equals, so we can do direct substitution right away. If our equation said x equals, we could do substitution. We would just plug it in for x instead of in for y. And this one's even easier because there's no coefficient on the y value. So let's number them. Equations 1 and 2, and we will be substituting equation 1 into equation 2 this time. So equation 2 says, well, it doesn't say y anymore. Now it's going to say 3x minus 3. That's our new y value. Minus 3x equals 1. And those parentheses aren't really doing anything for us. So we can combine like terms right away. And notice that this 3x minus this 3x, those cancel out, leaving us with a statement that says negative 3 equals 1. This is another one of those indicators like 8 equals 8, which is always true. Well, negative 3 equaling 1, that's never true. And this kind of a statement always makes me a little bit nervous, because either I'm on the right track and there's no solution to this problem, or I made an arithmetic mistake. In this case, we're on the right track. This problem is meant to illustrate that, that's an arrow by the way, that there is no solution. The cat likes to be held like a baby sometimes. It's a little weird. She's cute though, so it's okay. So this one's got no solution. Got to watch out for indicators like that. Negative 3 equals 1, or 1 equals 0, something like that. And then the last problem in this section worth of notes is a word problem, which is nice. All of us need a little extra practice with the word problems. So Alina has 24 coins made up of quarters and half dollars, and their total value is $10.75, and we want to know how many quarters does she have. The challenge with a word problem is always taking the English language and translating it into a mathematical statement. I was working with a student recently in a private tutoring session, and I said, "Do you speak Chinese?" And she said, "No." I said, "So if I asked you to take this question about Alina and her 24 coins and translate it into Chinese, could you do that?" She said, "No." I said, "It helps to know the Chinese language to do that." She agreed. It helps to know the mathematical language in order to do a translation from English into math. And for those of you who struggle with the mathematical language, if the process of solving a word problem is difficult, then you shouldn't be surprised, because you're still learning to better understand the mathematical language. So hang with this process and keep practicing, keep exposing yourself to challenging problems, and you'll get there. Just got to be patient with yourself. So Alina's got 24 coins. And the question is, how many quarters does she have? We don't know how many quarters or half dollars she has. So I'm going to say that Q is going to represent the number of quarters. And I will say that capital H is going to represent the number of half dollars. And now we're going to need to create a couple of equations, because this section is all about systems of equations. So I know that that's the goal, is to create a couple of equations to work with. One of the equations is based on the value of these coins. So quarters are worth 25 cents. So I'm going to say 25 cents or $0.25, 25 cents times the number of quarters, so that will be the total value. You have to bathe on my shoulder? Really? Is that what's happening? Thanks. 25 cents times the number of quarters. So if she had 5 quarters, she'd have $1.25 or 1.25. And then we're going to add to that a value of 50 cents times the number of half dollars she has. And this is going to equal her total amount of money, which we know is $10.75. I can't with you. You're impossible. Can you go all the way up maybe? Or all the way down? All the way, ow. Down, down, stop biting me. Why are you biting me? I feed you. Still biting. Ow. So this is an equation that's based on actual amounts of money, actual dollar values. You're going to run into problems like this, systems of equation problems, and we're going to have, I think, a whole section dedicated to word problems where you're going to be mixing different amounts of salt water or concentrations of soapy solutions, right, cleaning agents and things like that. So get used to the fact that these equations sometimes involve units. So the units in this first equation is dollars, and the second equation that we're going to create, let's label this equation 1. The second equation just has to do with number of coins. So we know that Q represents the number of quarters, plus H the number of half dollars, and the problem told us that we have a total of 24 coins. And that's our second equation. Is this immediately set up for substitution? Not so much. We don't have an equation that says Q equals or H equals. So we're going to have to create that. So let's come over here. We'll create another little column. And I'm going to subtract H from both sides. So that Q is equal to 24 minus H. That's still equation 2. Then I'm going to take equation number 2 and I'm going to plug it into equation number 1. Substitute 2 into 1. All right, substituting 2 into 1. All right, so I'm going to replace this Q on the bottom left corner of your screen. I'm going to replace this Q with, on the right-hand side of your screen, 24 minus H. Let's see what happens. 0.25 times our new Q value of 24 minus H. And then continuing on with equation number 1, we've got plus 0.50H equals 10.75. That's equation 1 because we substituted equation 2 into equation 1. Now we've got one equation with one variable. The variable is H, so we need to distribute, combine like terms, and solve for H. A quarter of 24 is equal to 6. So we've got 6 minus 0.25H plus 0.50H equals 1075. And then let's combine like terms. Negative 0.25H plus positive 0.5H equals positive 0.25H. And I'm going to subtract 6 from both sides because I'm a little short on space. And that equals 4.75 on the right-hand side. And then I'll divide both sides of my equation by 0.25 to finally get an H value of how many quarters are there in $1? How many quarters are there in $4? 16. How many quarters are there in 75 cents? 3. 16 plus 3, 19. So we have an h value, and now we can slide over and use, I'm so zoomed in, those equations got large, q plus h equals 24. We'll substitute this into equation 2. Q plus our h value, which we now know is 19, is equal to 24. Subtract 19 from both sides to find out that she has 5/4. This is an answer that you're probably not going to type in as an ordered pair. If you're using an online software, my guess is that you'll be given a couple of text entry boxes or maybe a multiple choice situation. Just make sure that you type the 19 and the 5 into their correct locations. And that's why I like using variable letters, in this case, variable names, that are appropriate, like Q for number of quarters and H for number of half dollars. That way, once I finally get to the end and I've got these couple of numbers, I know what they actually represent. And I highly recommend writing down what your variables actually represent so that you've got something to refer back to, because these problems can get a little lengthy, a little involved, and it's good to be sort of taking some notes, dropping some breadcrumbs as you go along. All right, the next time I see you will be in section 3, and I'm pretty sure over there we're going to be solving systems using the elimination or addition method, which is one of my favorites, and we need to be really good at that because it's necessary when we start solving systems of equations with 3 variables. Can't do that process without the elimination or addition process. So, take a deep breath. See you soon. Thanks, bye.